Hi guys, we're back to talk more about sedimentary rocks. This time we're going to talk about sedimentary environments. Okay, so sedimentary rocks form in particular environments. Not all environments around the earth are equally conducive to forming a sedimentary rock. For instance, the top of a mountain is a place where sediments aren't accumulating. Sediments that form there are rolling down slope and accumulating in valley bottoms and accumulating in riverbeds and floodplains and in shallow ocean environments. And so these low places on the landscape are generally the kinds of environments where sediments form. And when we think about where different kinds of sedimentary rocks are forming, it's very interesting to think about the fact that the environments that existed at some location in the past are not the same environments that exist there today. So for instance, we know that limestone is a rock that forms from the shells of marine organisms. And we know that these marine organisms are concentrated along coastlines, along reef environments, around the outside of islands. And when we go to places like the Grand Canyon in the southwest of the United States, there are these thick limestone layers. And the Grand Canyon of the United States is nowhere near a coastline today, but those rocks are many millions of years old, many hundreds of millions of years old in some cases. And so at the time when those limestone layers were forming in that location, that particular piece of rock was at a coastline. And so we can learn a lot about the history of the area by understanding the environment where a rock would have formed, which, just one more time to emphasize, does not mean that that's the same type of environment that exists in that location today. So we use a couple of different kinds of clues to help us understand about what the environment was like. And first of all, we kind of already talked a little bit about the idea of like sorting, and sorting happens because in like floodwaters, large sediments can be moved, but in slow moving water, only fine sediments can stay in solution, and the size of the sediment determines how easily they can move across the landscape and how far they're going to move across the landscape. And so we can learn a little bit about what was going on and in a particular location when we have like a breccia forming, which we talked about, was like a rock that's formed from all these angular, larger sized fragments that we can imagine did not move very far across the landscape, compared to like a conglomerate, which also has larger sizes but are a little bit rounded. So we can think about their transportation history that was probably more in like a riverbed environment, compared to like a siltstone or mudstone or shale. And we know that those fine sediments really don't settle out of a water column of the water unless that water has been sitting still for a really long period of time. And so that probably would have only happened like in an ocean environment or in a lake environment or a pond environment where the water is still for a long period of time. We can also think about what are clasts made of. Are they made of shells, like in the example of limestone I talked about before? Are they made up of like silica-based plankton shells, in which case they must have been coming from an ocean environment? Are they made up of plant matter that we think was accumulating in some sort of marshy environment? Are they made up of salts that we think probably were accumulating in some sort of desert environment or playa environment where we had these shallow lake beds that evaporate out water and allow different kinds of salts to accumulate in environments like modern day Border Town or modern day Great Salt Lake? And so basically all these kinds of thinking about like what are sedimentary rocks, what are they made of and how did they form, helps us understand, again, not what the environment is where that type of rock exists today, but what the environment was like at the time when the rock formed. And so, for instance, we know, as I just said, like breccia and conglomerates are probably going to be closer to mountainous areas where sediments are coming from. Evaporite rocks like halite and gypsum are probably going to be coming from more desert-like environments. Organics, things like peat, lignite, and coal are probably going to be coming from environments where we had like marshes or deltas where a lot of organic matter was getting buried in water and not breaking down as quickly as it would on land. So organic matter breaks down better where there's lots of oxygen. When it gets buried in water, it gets doesn't break down as fast and it accumulates in these marshy environments. Things like really fine sediment material, siltstone, mudstone, shale might form in like a lagoon or a delta or a floodplain or a shallow ocean environment. As we already mentioned, limestone is going to be existing in like reef environments or coastal environments. Sandstone might be also coastal environments or desert environments. Chert is probably more of an open ocean type of rock. So anyway, we can work backwards and understand the history of the landscape if we understand about these sedimentary environments. So sedimentary basins in general are these kind of low places on the landscape where sediments accumulate. And so there's different kinds of reasons why we might have a low place on the landscape. We might have like a coastal environment, which we would call like a passive margin basin. We might have different kinds of basins that are created from different tectonic stretching, like intercontinental basins or rifting basins, foreland basins, where the weight of a mountain belt is pushing down on the crust. So there's lots of different kinds of tectonic environments where we might have these sediments accumulating. And we're not going to get a lot into this concept, but it's something that's usually introduced when we start to think about where are sedimentary rocks forming. And so I just wanted to mention it briefly. Okay, another thing I do want to talk about in a little bit more detail because I find it pretty interesting is the idea of sedimentary facies. So this word F-A-C-I-E-S is pronounced facies. Facies are sets of sediments that are deposited at the same time in the same basin, but changes in the sedimentary environment occur laterally across a large basin, and different rocks are different, which leads to the kind of staggering of different rocks or different facies. And these different facies grade into each other laterally. Okay, so let me translate that. What does that mean? So for instance, we might have a series of rocks along a coastline where we have a sandstone region, a shale region, and a limestone region. These would all be rocks that formed around a similar period of time. It's not like the sandstone is all a lot older than the limestone or vice versa. And we call these different lateral side-by-side sections different facies. And when we get up a little closer and look at them in more detail, we can learn a little bit about what was going on in the environment as these facies were forming. But in order to help us understand this, we can refer to a law in geology that's called Walther's law, and it states that the vertical succession of facies reflects a lateral change in the environment. So what does that mean? Another way to say that would be when a depositional environment migrates laterally, sediments of one depositional environment come to lie on top of one another. So let me translate that now with a little bit with some pictures. So a transgressive facies or series of facies is when we have sea level that has encroached up onto the land. And so originally we had these side-by-side facies that I had mentioned before, like a sandstone, and then farther out to sea, we had some sort of siltstone. So this would have represented this very beachy environment. This would have represented a little farther out to sea where fine sediments are depositing. And this would have represented maybe some offshore reef environment where limestone organisms were accumulating. So we have these different, slightly different environments leading to different rock formations that are laterally situated side by side. And then sea level rise causes this lateral shift in where the environment is. So the shoreline that used to be here has now moved inland. And as a result, we start to see sandstone creeping up the landscape. We also start to see siltstone or shale shifting up the landscape and limestone shifting up the landscape. And the longer we wait, the more that is going to take place. And then if we start to kind of drill down over time and look at these different layers, we can see that limestone gets stacked eventually on top of shale, gets stacked on top of sandstone. And so this particular series is something that would indicate to a geologist, oh, in this time, and if we can date these rocks, we can learn when that was, but in this particular time, there must have been, first of all, this must have been a coastal environment, and then there must have been sea level rise occurring during this time. So it gives us clues about what was going on in the past. And so we might have that sea level rise occurring for a variety of different reasons. Maybe we had warming climate and melting glaciers. Maybe we had seafloor spreading. And so when the seafloor spreads rapidly, sometimes that actually lifts up the ocean floor and pushes the ocean water up a little bit. Or we can have the land sinking down as it gets heavier for a variety of reasons. But all these things might lead to a transgressive period in ocean history along this coastline, and then this particular series of finer grain material stacked on top of coarser grain material on the bottom. So the finer grain material representing the more marine types of rock, and the coarser grain material representing the more terrestrial forms of rock. And then this happens the opposite way during periods of sea level regression, or sea level, when the sea level is sinking. So that might happen when it's getting colder and more water is getting frozen up in terrestrial glaciers, when seafloor spreading slows and the ocean floor sinks, when the land is bouncing back up. We call that isostatic rebound, as it's losing weight for a variety of reasons. But this leads to the opposite effect, where we start to see the coarser materials from land be stacked on top of the finer grain material. So we might have limestone on the bottom, shale in the middle, and sand on the top. And so again, it just helps us give us little clues about the Earth in the past, because we don't have human records from these periods of time hundreds of millions of years ago, and we have to use these other clues to help us understand about the Earth's history. Okay, good stopping point.